This is the GCSE Physics Unit 3 pre-exam PowerPoint presentation that I will be delivering to my GCSE classes. I'd like you to remember that most of the formulas are on the equation sheet, so if you ever have a formula question in the exam, please refer to the equation sheet to make sure you're doing that correctly. I hope you enjoy this presentation. The first thing we're going to look at is refraction. Refraction is a change of direction of light as it passes from one medium to another. You should know the equation that the refractive index is equal to sin I over sin r. That is sometimes written as the equation where refractive index is equal to n equals sin I over sin r. You'll revise refraction as part of P1, and remember that you will have looked at how light changes direction as it moves from one material to the other. So in this diagram we've got the incident ray here. It comes in and strikes the surface. Because glass is more dense than air, it will slow down. As it slows down, it bends towards the normal. As it comes to the edge of the glass at this point here, it will leave the glass surface and it will speed up. As it speeds up, it will move away from the normal. You need to remember that we measure the angle between the incident ray and the normal ray shown there, and the angle of refraction is measured between the refracted ray and the normal as shown there. For this exam, and for this part of the exam in particular, you'll need to have a scientific calculator, as you'll need to do calculations involving taking the signs of numbers. And you can see that when you have a question, as the one shown here, where it says the angle of incidence is 32, the angle of refraction is 20, then you just substitute the numbers into the correct places. So we're going to do sine of 32 over sine of 20 and work out that the refractive index of this example is 1.55. Remember, because we're doing sines of values, we have no units for the refractive index. We're now going to look at lenses. A lens forms an image by refracting light. What you need to know about lenses is there's two types. There are converging lenses, as shown here, and there are diverging lenses, as shown here. A converging lens is also known as a convex lens. And what a convex lens does is it brings parallel rays of light, so you can see the light comes in parallel to the lens, and it brings them all to a focal point, or a principal focus. You need to be aware that the distance between the lens and f, and this point here, which is the principal focus, is known as f, which is called the focal length. Diverging lenses, like the one shown here, are sometimes known as concave lenses. They make light that comes in parallel diverge or spread out. And the way that they make it spread out, if you were to extrapolate the lines backwards, the real light rays that come this way, if you extrapolate them backwards, they make all those light rays appear as they came from one point, which we call the principal focus. And remember that the distance between the principal focus and the lens is known as f, which is also called the focal length. Both types of lenses have different uses. A converging lens can be used as a magnifying glass. The magnification produced by a lens is calculated using the equation shown below, where magnification is equal to image height over object height. This equation is available on the formula sheet, and you should always refer to the formula sheet throughout the exam if you're ever unsure about what equation to use. Now that we understand how the different lenses work, we need to be able to construct ray diagrams. So you should be able to construct ray diagrams to show the formation of images by converging and diverging lenses. You should then be able to discuss the nature of the images formed by the different types of lenses. When you discuss the images, you need to comment on three different things: their size, whether they're upright or inverted, or whether they're real or virtual. When you discuss the size of an image, you should comment on whether it is larger than the original object, so that will be enlarged, whether it's smaller than the original object, in which case it will be diminished, or whether it's the same size as the original object. When discussing whether or not the image is upright or inverted, you need to consider the direction of the original object. If the image is in the same direction as the original object, then it's considered to be upright. If it's in the opposite direction to the original object, it's considered to be inverted. When you look at whether or not the image is real or virtual, you need to decide on which side of the lens it's formed, and whether or not you could project that image onto a screen. Real images are formed where real rays cross, and the object can then be projected onto the screen. Virtual images form where the imaginary rays cross, and that image cannot be projected onto a screen. At the bottom of this slide we have a ray diagram for a diverging lens. Remember that a symbol for a diverging lens is this one, where you've got a straight line with two arrows pointing inwards, and that's the symbol shown there for a diverging lens. We will now move on to look at the ray diagrams for diverging lenses. The ray diagrams can be found at the bottom of the slide as shown here and here. When we construct a ray diagram for any lens, we need to draw two rays. The first ray is called the central ray, and the central ray goes from the top of the object, here, and through the central point of the lens. And you can see it's a straight line. That central ray has been drawn on this diagram as well, from the top of the object through the centre point of the lens, and again, it's a straight line. The next ray that you draw is the parallel ray. The parallel ray runs from the top of the object to the centre point of the lens, and it runs parallel to the principal axis, so it's a straight line. The principal axis is this dotted line here, so it's a straight horizontal line in both diagrams running from the top of the object to the central point of the lens. When light meets the lens, it is refracted, and in this case, the ray will be refracted through the principal focus. Now, a diverging lens will cause the ray to scatter or diverge, and so it will refract it from the principal focus on this side. So in order to draw that ray, you would put a ruler between your principal focus and where you'd finished the part of your ray so far, so the part of the parallel ray, and you draw a straight line along there, but you need to remember to make it dotted on this side. The dotted line indicates a virtual ray, so the ray doesn't actually come from this point, the lens just makes it appear as though it came from that point. The next part is to determine where your image is, and the image is formed where the two rays cross. So you can see our image formed by diverging lens is there, and the image formed by this diverging lens is there. You'll then probably be asked to talk about your image and compare it to the object. So in both cases, or in all cases for diverging lenses, the image that is formed by a diverging lens is always smaller, because it's smaller than the object. You can see that the size is decreased in each case. It's got smaller than the object. It's virtual, because it's formed on the left-hand side of the lens. It cannot be projected onto a screen, and it is formed where the imaginary rays cross. The image is also upright because it's in the same direction, it's pointing in the same direction, which is upwards, as the original object. We'll now look at the ray diagrams for converging lenses. A converging lens has a symbol as shown in the top right-hand corner here, and a converging lens has a symbol with a straight line with two arrows pointing outwards. There are two types of ray diagrams for converging lenses. The first one we're going to look at is when a converging lens can be used as a magnifying glass. A converging lens can be used as a magnifying glass when the object is closer to the lens than the principal focus. So you can see the principal focus is this point here. The object is between the lens and the principal focus. When the object is between the principal focus and the lens, then the lens will act as a magnifying glass. As before, you draw two rays when you construct your ray diagram. The first one is a central ray that goes from the top of the object through the centre point of the lens and is a straight line. The second ray is a parallel ray. Remember, it runs parallel to the principal axis, which is this bit here, and goes from the object to the centre of the lens, running parallel to the principal axis. Once it gets to the centre of the lens, remember it's refracted, and this time it's refracted through the focal point. And you can see the focal point is that dot there. So all you need to do now is using a ruler is to join up this point here and this point here at the focal point. And that completes your parallel ray. Now looking at those two rays that we've drawn so far, it's clear that they will never cross. So we'll never be able to form a real image because the two light rays won't cross. They'll continue getting further and further apart. But if we were to add an eye, here's my eye drawing, and if that observer was looking at those rays, well, he would see them coming from this point here. So if you extrapolate them back, which is what this dotted line is showing, you would see those two rays coming from that point there. So you can see we can form a virtual image appearing to be inside the lens as shown by this line here, which is where the two virtual rays cross. The next point is to discuss how the image compares to the object. So you can see in terms of size, well, the image is much higher, so it's it's enlarged. You can see that it's been formed by virtual rays or imaginary rays, and it can't be projected onto the screen, therefore it's a virtual image. And you can also see it's in the same direction as the original object, so it's upright. The final example we're going to look at is for a converging lens when the object is actually further away than the focal point. So you can see that the focal point is now between the object and the lens itself. In this case, you do the same thing as before. You draw a central ray, which is straight through the centre of the lens. You can draw a principal ray, which is parallel, remember, to the principal axis, to the lens, and then goes through the focal point here. But in this case, those two rays cross. And so your image is formed in that position there, where those two rays cross. I've also included a third ray. You don't need to always include the third ray on the exam, which is a focal ray. But if you want to understand how to use that, remember it just goes through the focal point first, and then it runs parallel. And you can see that ray crosses as well. So the final thing that's left for us to do is discuss how this image, this one here, compares to the object. Well, you can see in this case, it's the same size as the object. It's real because it can be projected onto the screen, and it's formed where the real rays cross. And also, it's inverted because it's the opposite way around. So it's pointing downwards as opposed to up, which is the way the object was pointing. so we consider that ray to be inverted. On this slide we're going to look at the human eye. What you need to know about the human eye is that the near point of the human eye is approximately 25 centimetres, and the far point of the human eye, so the furthest away the human eye could see, if there's a light beam sent from that position, would be infinity. You also need to be aware of the different structures of the eye and what roles they fulfill in allowing us to be able to see. So the first thing we've got here is a ring of muscles, and the ciliary muscles. They control the shape of the lens by contracting and relaxing. And obviously when they are relaxed, the lens is least curved, so it's least powerful, and when they contract, the lens is most curved and it's most powerful. The pupil is a hole in the iris that lets the light in, like the aperture of a camera, and it automatically responds to light levels. So it will grow larger if there's lower light levels, and it will grow smaller if it's very bright. The cornea is a thick layer of transparent cells that protect the eye and are the principal means of focusing the rays by refraction on entering the eye. So they fine-tune the focusing done by a lens. So it will start to be focused by the cornea, but then the lens takes over. So you can see the lens is this part here, okay, and that focuses the rays onto the retina at the back of the eye, which is this point here. Now, the retina is a layer of light-sensitive cells that changes light energy into electrical signals, which are then carried along the optical nerve to our brain. Finally, the iris is a coloured ring of muscles that controls the size of the pupil. So remember that the pupil's size will change depending on the brightness of the light, and the iris is the coloured ring around there that controls the size of the pupil. So we can now look at how we can correct vision using lenses. So if you're short-sighted, the reason for that is that your lens is usually too powerful, or your cornea is too curved, or your eyeball's too long. And what that basically means is that you're bringing your light rays into focus in the centre of your eye, rather than on the back of the retina. This makes distant objects appear blurred, and close objects will remain in focus. So to correct short-sightedness, what we need to do is we need to spread the light out more before it enters the eye. So to do that, we use a diverging lens, okay, or a concave lens, and we're going to spread the light out as shown in this part here. So you can see there's a diverging lens. We can spread those light rays out slightly so that our super powerful lens will bring it into focus on the retina at the back of our eye, and we'll be able to see things clearly. Long-sightedness is caused by lenses being too weak, or the cornea not being curved enough, or the eyeball being too short. So essentially what's happening in this case is the lens isn't powerful enough to bring the rays into focus on the back of the retina. So instead they're brought into focus at this point here, rather than on the back of the eye, which is the retina, where those light-sensitive cells are. So to correct long-sightedness, what we need to do is use a convex lens, or a converging lens, which will start bringing the light rays into focus sooner. So you can see here, there's our converging lens. We'll bring the light rays into focus soon before it even hits our lens, and our lens does the rest of the work in bringing it to converge onto the back of our eye, which is our retina there. So lenses have different powers. The power of a lens is given by the formula P equals 1 over F, where P is the power measured in diopters and F is the focal length measured in meters. The focal length of the lens is determined by the refractive index of the material from which the lens is made and the curvature of the two surfaces on the lens. So for a given focal length, the greater the refractive index, the flatter the lens. This means that the lens can be manufactured thinner. We can compare the eye and the camera. The eye and the camera are similar because they both have a converging lens. They both produce an inverted real image. So in an eye that's formed on the retina, whereas in a camera that's formed on the charge coupled device or CCD, or in old-fashioned cameras on the film. They can both control the amount of light entering them. In the eye this is done by the pupil, whereas in the camera this is done by the aperture. Finally, they can both be changed to bring objects into focus. To do that in the eye we use the ciliary muscles, whereas to do that in the camera we use something like the zoom. Just to make you aware that you should be able to link parts of the eye to parts of the camera and explain how they're similar and how they're different. We will now move on to look at medical applications of light. So the first thing we need to understand is total internal reflection. Total internal reflection occurs when light is passing from a more dense medium to a less dense medium, and the angle of incidence is greater than what we call the critical angle. With total internal reflection, instead of the light refracting out and coming out of the material, it's actually reflected and kept within the material, as shown in this diagram here. Total internal reflection allows visible light to be sent along optical fibres, and this has uses in medicine such as endoscopes, so you can send an optical fibre down someone's mouth into their stomach, for example, and then we will be able to use total internal reflection to pass the light back up to the eyepiece and be able to see inside their bodies without cutting them open. The final medical application of light is that the laser can be used as an energy source for cutting, cauterizing and burning, and one example of that is laser eye surgery. A further application of physics in medicine is X-rays. Remember that X-rays are part of the electromagnetic spectrum, which is shown in this diagram here, starting at radio waves and going all the way up to gamma. You can see that X-rays are here, so they have a very short wavelength and they cause ionization, which you must remember can damage cells and lead to cancer. Therefore, precautions must be taken when we use X-rays, so things like having the person taking the X-ray photo out of the room, putting lead lining over the patient so only certain areas of the patient are exposed to the X-rays, and making sure that people aren't having too many X-rays in a given time frame. The use of X-rays in medicine is for diagnosis of bone fractures and dental problems. They can also be used in computerized topography or CT scans. You should remember that CT scans allow doctors to build up a 3D image of internal parts of the body, and sometimes they need to use a contrast medium, which is something that absorbs X-rays, in order to do that. In order to use CT scanners and also to form digital images of X-rays, we need to use something called charge coupled devices, or CCDs, and what CCDs do is they convert X-rays into a digital image. The final use of X-rays in medicine is the idea of them being used to kill cancer cells, which is known as radiotherapy. So now look at ultrasound. You should be aware that electronic systems can be used to produce ultrasound waves which have a frequency higher than the upper limits of hearing for humans. You should also know that the range of human hearing is about 20 Hz to 20,000 Hz. You should also be aware that ultrasound waves are partially reflected when they meet a boundary between two different medium. The time taken for reflections to reach the detector can be used to determine how far away such a boundary is. So you can see that I've just drawn a very brief graph here showing intensity, I, going up the axis, and time along here. And you can see that you'd end up with two peaks. That's the initial peak you sent out, and this is the return peak. And you can use the time between the two. So you can use the time between the two to work out the distance that is travelled if you know the speed of the ultrasound wave. To do that calculation, you need to use the equation that's represented here. The equation is S equals V times T, where S is the distance measured in metres, V is the speed in metres per second, and T is the time taken, measured in seconds. You also need to be aware that ultrasound waves can be used in medicine, and you should include the examples that they can be used to destroy kidney stones, and they should also be used in prenatal scanning. Now let's look at centre of mass. The centre of mass of an object is a point at which the mass of the object may be thought to be concentrated. So in physics it's nicer to simplify things down, so rather than thinking of something that's quite big and bulky, we like to think about how it would act from the centre of mass. If you want to locate the centre of mass, you can freely suspend an object, and it will come to rest with its centre of mass directly below the point of suspension. So if we've got an irregular shaped object like this one here, if we hang it from a nail, and then hang a plumb line, we know that along that plumb line, somewhere, will be the centre of mass. So we can now rotate the object, and once we rotate it, again we'll hang the plumb line, we'll draw a line along the plumb line, and somewhere along the plumb line will be the centre of mass. And where those two lines intersect, because we've already drawn one, we will see the centre of mass of the object. The centre of mass of a symmetrical object is along the axis of symmetry. So you can see you've got some symmetrical objects here, so you've got the circle, and the centre of mass will be directly in the centre. If we look at a triangle, we can draw symmetrical lines on, and it will be in the centre of symmetry, and again, with something like a rectangle. You should also know that objects with a wide base and a low centre of mass are more stable than those with a narrow base and a high centre of mass. So you can see of the two objects we've got here, we've got the champagne flutes compared to this vase. The vase is more stable because it's got a wide base and it's got a low centre of mass, compared to these that have got a narrow base and a higher centre of mass. We're now going to look at pendulums. You should know that for a simple pendulum, the time period is equal to 1 over the frequency, as shown in the equation up here. Remember that time period is measured in seconds and frequency is measured in hertz. The time period for a pendulum depends on its length only. So if you increase the length of the pendulum, we'll increase the time period for that pendulum. And you should be aware that there's no other factors that you need to consider that will affect the time period of the pendulum other than its length. You should be aware of a few simple examples of pendulums being used in clocks, fairground rides, and also on swings and other playground rides. So we now move on to look at moments. The turning effect of a force is called the moment, and the size of the moment is given by the equation that's shown there, which is that the moment is equal to force times the perpendicular distance from the pivot. You can see in the example here that we've got the force acting this way, so the distance must be perpendicular. When we mean perpendicular, we mean at right angles to the force. If an object's not turning, the total clockwise moment must be exactly balanced by the total anti-clockwise moment about any pivot. So if you look at the seesaw example, we can see here, there's the pivot. This person's pushing the seesaw down, so he's rotating it anti-clockwise, and this boy is pushing it down that way, so he's rotating clockwise. The fact that they're not moving means that the clockwise moment must equal the anti-clockwise moment, and so you can see here that the larger mass person on this side must be closer to the pivot compared to the small boy who's further away from the pivot because he's got a smaller mass. You also need to be aware that if the line of action of the weight of an object lies outside the base of the object, there will be a resultant moment and the body will tend to topple. So what that means is, for this elephant, we must have the idea that its centre of mass must be directly above the ball there, in this case, and therefore his line of action for his centre of mass must be going over the ball. However, if the centre of mass of that elephant shifted slightly, so that his centre of mass was now outside the edges of the base that it's got there on the ball, then that elephant would topple and fall over. So now I'm going to apply our knowledge to a moments question. It says in the question that on a seesaw, Mary, with a weight of 600 newtons, balances John, with a weight of 200 newtons, when she sits 1.5 metres away from the pivot. How far from the pivot is John? So you can see here we've got a distance of 1.5 metres, and we got here she's got a weight of 600 newtons. If they're balanced, then their moments are going to be equal to one another. John's got a weight of 200 newtons. So we're going to have to apply the principle of moments in order to work this out. So the principle of moments states that Mary's weight times her distance is going to be equal to John's weight times his distance from the pivot. So we can put that into the equation showing that 600 newtons times 1.5 is equal to 200 newtons multiplied by the distance to John. So you can simplify this and then rearrange it. So we get 900 is equal to 200 times the distance to John. So therefore 900 divided by 200 gives us our distance to John. And we can find that John is 4.5 metres from the pivot. You also need to be aware that levers can be used as a force multiplier. So by using a lever at a longer distance, you can increase the force that you're applying on the far end of the load. We'll now look at hydraulics. The key thing to understand in hydraulics is to understand that liquids are virtually incompressible, which means you can't really squish them any more than they already are. And that means that the pressure in the liquid is transmitted equally in all directions. If I apply a force to the liquid on this smaller piston here, as I've shown there, then the liquid will be compressed, but it can't compress, so it will exert a pressure through the liquid and then it will push up at this side here. And you can see now that the use of different cross-sectional areas on the effort, which is this side, and the load side of the hydraulic system enables the system to be used as a force multiplier. So by having a smaller cross-sectional area here where I apply my force, I can get a larger force acting on the load side over on this side here. To work these questions out then, pressure is equal to force divided by area. That's the unit you've got there. And the unit of pressure is pascals, or PA. And if you were to apply this to a question, you can see a force of 25 newtons applied to a smaller cylinder of hydraulic press. If the area of the cylinder is 8 cm squared and the area of the large cylinder is 100 cm squared, what is the force exerted by a large cylinder? So the answer to this question can be found in the bottom part here. The first thing to point out is that as both my areas are in centimetres squared, I can keep my areas as centimetres squared and I do not need to convert. So the first thing that I do is I work out the pressure experienced by the liquid. I do that by working out having the force applied to my effort divided by the area of my effort piston. So I work out pressure is 25 divided by 8, which gives me 3.125 newtons per centimetre squared. Notice I can't put that in pascals because I haven't had my area in metres squared. So I have to keep it as newtons per centimetre squared. I then know that pressure will be the same throughout the liquid, and so therefore that pressure will be exerting a force on this piston here. That piston has an area of 100 centimetres squared, so I can set that into my equation now. So my pressure is 3.125, my force is unknown, so it's F, and that's divided by 100 centimetres squared. So to work out F, I do 3.125 multiplied by 100, and that gets me 312.5 newtons. So you can see that for a force of 25 newtons applied here, I experience a force much greater because it's been multiplied by using different areas and my hydraulic system. We'll look at circular motion now, and you can see with circular motion it applies to any object that moves in a circle, and when an object moves in a circle it continuously accelerates towards the centre of that circle. This acceleration changes the direction of the motion of the body, but not its speed. So you can have an object moving at constant speed around a circle, but because it's accelerating, its direction and velocity will be changing. The resultant force causing this acceleration is called the centripetal force and is always directed towards the centre of the circle. The centripetal force needed to make an object perform circular motion increases as the mass of the object increases, the speed of the object increases, and the radius of the circle decreases. If you are asked to draw the direction of the centripetal force, remember it always acts as a straight line towards the centre. I've drawn that on there and on that one at the top, so in terms of that one. And you could sometimes be asked to explain what gives rise to the centripetal force. Remember, the centripetal force is just a name of the force that's acting towards the centre of a circle. It's not really a force in the real sense of something like friction or gravity. Those two forces cause the centripetal force to exist. So if we look at each case here then, so we've got the friction acting on the car as it goes around a corner. The friction is what causes the centripetal force. So centripetal force is caused by the friction. In this case, where we're swinging a bucket around on a rope, the force that's acting towards the centre there is actually caused by the tension, and that gives rise to centripetal force. If we've got the moon orbiting the Earth in this case, the centripetal force is caused by the force of gravity between the moon and the Earth. If you want to talk about the electrons orbiting the outside the atom or orbiting the nucleus, what holds them in place? Well, that force is the electrostatic force. We're now moving on to the final part of P3, which is Unit 3.3, which is all about electromagnetism. So electromagnetic induction is the first thing that we really need to understand. So if an electrical conductor cuts through a magnetic field, a potential difference is induced across the ends of the conductor. Or, if a magnet is moved into a coil of wire, a potential difference is induced across the ends of the coil. These ideas have completely revolutionised the world. The idea that if you move a magnet into a coil of wire, you could produce a potential difference across the coil of wire, and that causes an electric current to flow, is the basis of how we generate all our electricity that we use in our houses today. So if you look at the two examples here, as we move the magnet through there, what we would see is we would get a reading as that magnet falls through the coil on our voltmeter here. And in this case, if we move this coil of wire down through the magnet, we would see the ammeter reading move as well. So we'd be inducing a potential difference across the coil of wire that would cause a current to flow, which we could read on our ammeter, which is this part here. One application of electromagnetism is the use of a transformer, and you'd be expected in the exam to be able to explain how the transformer works. And these are the points that you need to include. So an alternating current in the primary coil produces a changing magnetic field. So we send the current around the primary coil, which is this bit here, that causes a changing magnetic field in the iron core. This magnetic field links with the secondary coil, which induces an alternating potential difference across the ends of the secondary coil here and here. That alternating potential difference causes an alternating current to flow through that wire. Now, transformers will only work if you use an alternating current, because only an alternating current then could cause a changing magnetic field. There are two types of transformers that you need to know about. The first one is a step-up transformer. The step-up transformer increases the potential difference across the secondary coil. It does that by having more turns on the secondary coil. So you can see the number of turns on this side is greater than this side. Step-up transformers are used at the start of the national grid to step up the potential difference before it's transferred through the power cables. And they do that because they've got a greater number of turns on the secondary coil. A step-down transformer has a lower potential difference on the secondary coil, and it does that by having more turns on the primary coil, as you can see here, than it does on the secondary. So a step-down transformer, the potential difference across the secondary coil is less than the potential difference across the primary coil. In each case, you need to know that when you increase or decrease potential difference, you do the opposite to current. So a step-up transformer decreases the current, whereas a step-down transformer increases the current. You can see here there are some transformer calculations. The potential difference across the primary and secondary coils of a transformer are related by the equation that Vp over Vs, which is the potential difference on the primary divided by the potential difference on the secondary, is equal to the number of turns on the primary divided by the number of turns on the secondary coil. That equation will be given to you on the equation sheet. Now, if we assume that transformers are 100% efficient, electrical power output would be equal to electrical power input, and therefore we can use the equation that's shown here, that Vp times Ip, so that's the potential difference on the primary coil multiplied by the current on the primary coil, is equal to the potential difference on the secondary coil, Vs, multiplied by the current in the secondary coil, IS. So we can now apply our understanding to an example. So if the primary coil has 10 turns here, and then 230 volts AC, the secondary coil has a voltage of 460 volts, how many turns must it have? So because we're talking about number of turns and voltage, we're going to use this equation here. So you can see that Vp over Vs is equal to Mp over Ns. So you can put those numbers in and get 230 over 460 equals 10 over M. S. We can then all just swap them round, and we end up getting Ns is equal to 4,600 over 230 to give us 20 turns. So the final thing we're going to look at now is comparing transformers. There are two types of transformers you need to be aware of. One's the normal type of transformer we looked at already, and the other is a switch mode transformer. A switch mode transformer operates at a higher frequency, often between 50 and 200 kHz. Switch mode transformers are much lighter and smaller than traditional transformers, working from a 50 Hz main supply. So switch mode transformers use very little power when they are switched on, but no load is applied. So most of the transformers we tend to use in our households now are switch mode transformers. That brings us to the end of the presentation. Thank you very much for listening. I hope you found it useful. Goodbye.